And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang.
The James Webb Space Telescope has made a groundbreaking discovery regarding the rate of expansion of the universe, and it's causing quite a stir in the world of cosmology. Essentially, what it found has only deepened a long-standing problem known as the Hubble Tension. Picture this. Our best models of the cosmos predict a certain rate at which the universe should be expanding. But according to the observations made by the Webb Telescope, the universe seems to be expanding at a much faster rate than what we anticipated. This discrepancy is baffling because it challenges the very core of our understanding of how the universe works. In the past, astronomers thought that this difference could be chalked up to technological limitations. They hoped that with better tools like the Webb Telescope, we'd get a clearer picture and resolve this tension. However, instead of clearing things up, the Webb Telescope has only intensified the mystery. It's as if there's a piece missing from our puzzle, something crucial that we're not grasping in our calculations or observations. So, what exactly is this Hubble tension, and why is it causing such a commotion among astronomers? Well, put simply, it's the stark contrast between what our models predict about the universe's expansion rate and what we actually observe. The James Webb Space Telescope's findings have only underscored the gravity of this situation. It's like shining a spotlight on a problem we were hoping would go away, only to find it glaring back at us, more puzzling than ever. Now the big question is, what does resolving this Hubble tension entail? If we could crack this cosmic conundrum, it would likely require us to delve into new realms of physics. It's like peering into the unknown, where the answers could potentially reshape our understanding of the universe itself. To truly grasp the magnitude of this crisis, we have to rewind the clock back a century to the 1920s, where the seeds of our modern understanding of the cosmos were first sown. Back in the day, there was a big showdown in the astronomical world known as the Great Debate, starring two astronomers, Harlow Shapley and Herbert Curtis. Their battleground? The size of the universe. It all boiled down to a simple yet profound question. Was our Milky Way galaxy the whole shebang, or were there other galaxies out there expanding the universe far beyond our wildest imagination? Now, you might scratch your head at this today, but back then, the prevailing belief among astronomers was that our universe was contained within just one galaxy, the Milky Way. Sure, we had glimpses of other celestial bodies, like the Andromeda Galaxy, but they were mostly considered part of our own galactic backyard. They were labelled as spiral nebulae, not galaxies, simply because they seemed like star clusters within the Milky Way. So, the big fuss was over whether these spiral nebulae were cozying up within the confines of the Milky Way, or if they were actually galaxies unto themselves, chilling out in the vast expanse of space. Shapley threw his weight behind the idea that the Milky Way stretched about 300,000 light-years across, with all the stars and systems snuggled up neatly inside. Essentially, he argued that the Milky Way was the be-all and end-all of the universe. Curtis, however, had a different take. He boldly claimed that these nebulae were independent galaxies, just like our trusty Milky Way, but way, way out there in the cosmic boonies. The showdown went down on April 26, 1920, and it was a clash of titans, each with their own vision of the universe. The debate left astronomers scratching their heads because, well, nobody seemed to have a definitive answer. Enter Edwin Hubble, the hero of our story. While Shapley and Curtis duked it out, Hubble was quietly making history. Armed with the most powerful telescope of his time at the Mount Wilson Observatory, he made a jaw-dropping discovery that would settle the debate once and for all. As Edwin Hubble peered through his telescope into the depths of space, he stumbled upon a revelation that would shake the foundations of our understanding of the universe. At the time, the Andromeda Nebula was thought to be a mere speck within our own Milky Way galaxy. But Hubble's careful observations of Cepheid variable stars, particularly one named V1 within the Andromeda Galaxy, revealed something extraordinary. The distance between us and V1 was roughly 1 million light-years, a distance about 3 times greater than what Shapley had estimated for the size of the Milky Way. This groundbreaking finding confirmed Curtis's theory that the spiral nebulae were indeed separate galaxies, akin to our own Milky Way. However, this revelation wasn't just a stroke of cosmic curiosity. It set off a chain reaction of new questions and discoveries. Hubble continued to delve into the mysteries of the universe and noticed a fascinating trend. Galaxies scattered throughout space appeared to be moving away from us, and the farther they were, the faster they seemed to be speeding away. This observation led to a simple yet profound relationship. The velocity at which a galaxy is receding, denoted by v, is directly proportional to its distance from us, represented by d. This seemingly innocuous equation gave rise to one of the most contentious numbers in the field of astronomy, the Hubble constant. This constant is essentially the cosmic speed limit, telling us how quickly a galaxy is zooming away from us for every megaparsec it is distant. And for those unfamiliar, a megaparsec is a unit of distance equivalent to about 3.26 million light-years. To grasp this concept, let's take a simple scenario. Imagine we're observing 2 galaxies. Galaxy A is 1 megaparsec away from us, while Galaxy B is double that distance at 2 megaparsecs. If the Hubble constant is, say, 70 K light-years/s/mpc, then Galaxy A would be drifting away from us at a rate of 70 km per s. Galaxy B, being twice as far, would be speeding off at double that rate, 140 km per s. This straightforward relationship is the cornerstone of our understanding of the expanding universe, a fundamental piece of the puzzle that the James Webb Space Telescope is now shedding new light on. The universe's expansion isn't a result of galaxies physically darting through space. Rather, it's the fabric of space itself stretching. Essentially, the Hubble constant gives us the scoop on just how briskly the universe is stretching out. But here's the rub. It seems like a simple math problem, right? Measure the distance to a galaxy, call it d, clock its velocity of recession, let's call that v, then plug and play to find the Hubble constant. Easy peasy. Well, if only it were that straightforward. Pinpointing how swiftly a galaxy is cruising away is a cinch. Just decipher its redshift and crunch some numbers. But nailing down the distance? That's been the cosmic conundrum. How in the universe do you accurately gauge the distance to a galaxy light-years away? Astronomers got clever with it. They enlisted a particular group of stars called Cepheid variables. These stars have a neat trick up their cosmic sleeves. They pulsate in a rhythmic fashion, brightening and dimming predictably. Back in the early 1900s, Henrietta Swan Leavitt turned her gaze to the heavens and clocked plenty of Cepheid variables in the Magellanic Clouds. Her keen eye unveiled a vital link between their pulsation patterns and luminosities. The longer a Cepheid star pulses, the brighter it shines. So, if you're itching to measure the distance to a galaxy, just follow this cosmic recipe served up in 3 steps. The first step is all about watching the beat. Astronomers train their telescopes on a Cepheid variable tucked away in some far-off galaxy and meticulously time how long it takes for the star to dance through one full cycle of brightening and dimming. Because this pulsation period is directly linked to the star's brightness, we can whip out the period-luminosity relation to figure out just how luminous the star truly is. This luminosity, known as the absolute magnitude, gives us the real scoop. So, if our star struts its stuff over 30 days for a full cycle, its absolute magnitude, its genuine luminosity, clocks in at a cool minus 4.85. Next up, we're comparing what's seen with what's real. Telescopes help us gauge the star's apparent brightness, how dazzling it looks from our vantage point on Earth. Let's say it twinkles at a magnitude of 24. Here's a mind-blowing tidbit. The human eye can barely pick up stars beyond a magnitude of 6, so our star in the example is roughly 16 million times fainter than what we can catch sight of without the aid of technology. Now, on to the grand finale, the brightness distance tango. This is where the cosmic enchantment kicks in. There's a golden rule in astronomy. Armed with the true brightness and the apparent brightness, you can bust out a nifty equation called the distance modulus equation to pinpoint the star's cosmic digs. So, we've danced through our 3 steps: timing the star's pulsation, uncovering its true brightness, measuring its appearance from Earth, and then, with a stroke of cosmic arithmetic, we unveil its cosmic address, a cozy 5.9 megaparsecs away. Voila! With just one star of the right kind, we've managed to sleuth out the distance to the entire galaxy it calls home. Instead of relying solely on cheap-eyed variables, astronomers also harness the power of Type 1, A supernovae, to gauge the distance to their galactic hosts. While Cepheids excel at measuring distances within tens of megaparsecs, Type 1, A supernovae step up to the plate for distances spanning hundreds of megaparsecs. Sometimes, astronomers blend both methods to double-check their distance calculations. Thanks to advancements in technology and precision measurements, astronomers have landed on a Hubble constant value of approximately 73.4 kilometers per second per megaparsec, primarily derived from observations of Cepheid variables. But how did they nail down this number with such certainty? Well, truth be told, they didn't. That's precisely why they turned to cosmological models for validation. If their calculations aligned with these models, it would signal a victory for our understanding of the expanding universe. However, any discrepancies would signify a fundamental glitch in our comprehension of the cosmos. Enter the cosmic microwave background, CMB, a relic from the Big Bang era. This faint glow, lingering from the universe's infancy, offers a glimpse into its state a mere 380,000 years post-Big Bang, before the formation of stars and galaxies. Unlike the cosmic distance ladder, a sequence of steps astronomers use to gauge cosmic distances, measurements from the CMB provide an independent avenue for verification, allowing astronomers to cross-reference results obtained from Cepheids and supernovae. To chart the cosmic microwave backgrounds, CMB, subtle temperature fluctuations across the celestial canvas, astronomers deploy spacecraft like WMAP and Planck. These nuanced variations reflect density disparities in the early universe and are intertwined with a slew of cosmological parameters, including the universe's expansion rate. When astronomers compared Hubble constant values derived from these CMB observations with those from Cepheids and supernova, they anticipated harmony. However, they stumbled upon an unexpected twist. The Hubble constant value derived from the CMB method clocked in at approximately 67 km/s/MPC, a tad lower than the figure obtained through Cepheids and supernova. Though this discrepancy may seem slight, it carries significant statistical weight, surpassing the anticipated margins of error for such precise measurements. This disparity births the Hubble Tension, a monumental quandary in cosmology. Essentially, it pits the observed expansion rate of our local cosmic vicinity against the expansion rate deduced from early universe conditions. Astronomers held out hope that perhaps the perceived gap could be chalked up to the resolution limitations of the Hubble and other mammoth telescopes. Their optimism soared as they awaited insights from the James Webb Space Telescope, anticipating that its infrared gaze might quell the crisis. Yet, the results dashed their hopes, solidifying their worst fears. Cepheid variable stars, typically nestled within densely populated stellar neighborhoods, present a unique challenge. Their company of surrounding stellar objects complicates the measurement of their brightness, casting shadows on the accuracy of distance estimates. A prime instance is a distinct crimson speck pinpointed as a Cepheid variable nestled within NGC 5584. Captured in images by the Hubble Space Telescope's Wide Field Camera 3, this hazy object emerges amidst a bustling backdrop of celestial neighbors. Conversely, images snapped by the Webb Telescope, armed with its superior infrared prowess, offer a sharper view, portraying the same Cepheid variable with heightened clarity and notably as a discrete entity set apart from its neighbouring stars. Scientists have keenly observed numerous Cepheid variables within two galaxies, NGC 4258 and NGC 5584. NGC 4258, being relatively close, boasts a well-documented distance. Meanwhile, NGC 5584, home to the Type 1, a supernova SN1A 2007 AF, stands as a distant host to Cepheid variable stars. Over 320 Cepheid variables hailing from these galaxies underwent scrutiny using both the Hubble and James Webb Space Telescopes to assess and juxtapose their capabilities. The depiction in the research paper showcases the arrangement of each variable star in NGC 4258, with their pulsation periods spanning from 18 to 41 days. The Hubble images are marked in black, contrasting with the magenta highlights indicating the Webb images. While the Hubble images appear congested, the Webb images, owing to their superior resolution, offer a less cluttered view. This distinction forms the crux of the research paper's aptly coined title, "Crowded No More." Likewise, snippet images from both telescopes found in NGC 5584 are exhibited for all Cepheids with periods ranging from 39 to 43 days, indicative of the brighter Cepheids. Through these observations, the period-magnitude relationship was delineated for both galaxies, as depicted in the accompanying panels. The data points highlighted in red stem from the Webb filter, while the grey dots represent observations from the Hubble Space Telescope filter. And what's the revelation? This comparative analysis demonstrates that the red data points adhere to the same trajectory as the grey ones, showcasing a consistent trend across observations. However, a noticeable decrease in the standard deviation is evident for both galaxies. A diminished standard deviation signifies reduced error, a trend prominently observed in the Webb data points. To corroborate these findings, the same research team expanded their observations to encompass larger samples of Cepheid variables and supernovae across a total of 6 galaxies. To their astonishment, they consistently obtained results that corroborated the existence of the Hubble tension. Based on this comprehensive analysis, the team confidently dismissed measurement error as the root cause of the Hubble tension. Thus, the observations conducted by the James Webb Space Telescope have validated the established value of the Hubble constant, underscoring the crisis in cosmology. This suggests that the Hubble tension does not stem from technological constraints or uncertainties in measurement. Instead, it exposes a gap in our foundational comprehension of the universe. Now that the James Webb Space Telescope has substantiated the presence of the Hubble tension, the precise nature of the discrepancy remains elusive. It's plausible that inaccuracies in distance measurements or shortcomings in our understanding of the cosmic microwave background contribute to this disparity. It's even conceivable that both values harbour flaws, with an unidentified factor at play. Resolving the Hubble tension is pivotal for 3 key reasons. Firstly, it serves as a litmus test for the standard model of cosmology. The Hubble tension could signify a potential flaw in the lambda cold dark matter model, the prevailing paradigm in cosmology. This model integrates the cosmological constant and cold dark matter to elucidate the evolution and structure of the cosmos. If inaccuracies within this model underpin the Hubble tension, addressing it could prompt significant revisions to our cosmological understanding. The second reason is delving into the enigmatic realm of dark energy. Accounting for a whopping 68% of the observable universe, dark energy remains a perplexing force propelling the universe's accelerated expansion. The Hubble constant stands as a direct gauge of this expansion rate. Therefore, discrepancies in its measurement could yield fresh insights into the essence of dark energy. Lastly, comprehending the pace of cosmic expansion holds the key to forecasting the fate of our universe. Divergent expansion rates may herald varied scenarios, ranging from an eternal expansion where galaxies drift further apart to a big crunch, culminating in the universe's eventual collapse, or even a big rip, tearing the fabric of space-time asunder. Resolving the Hubble tension marks a crucial stride towards deciphering our cosmic destiny. To that end, astronomers are exploring diverse independent methodologies to gauge the universe's expansion rate. One avenue involves scrutinizing gravitational sources like merging black holes or compact objects coupled with optical light emissions. Another tactic entails measuring the distance to red giant stars by observing their helium flash, which provides a precise marker for their intrinsic luminosity. Nevertheless, astronomers must ascertain the accuracy of these and other innovative techniques. As the intensity of the Hubble tension mounts, it beckons a myriad of possibilities that could pave the way for a profound comprehension of the cosmos. Recently, the James Webb Space Telescope unveiled the discovery of the farthest black hole, poised at the very edge of time. If you missed out on this captivating episode, be sure to catch up on this thrilling revelation.